In this video, we're going to cover a fourth part of the chapter on functions. So this was just added because I had forgotten about it. So sorry about that. So we talked before in the first video about the built-in functions we can use primarily from the CMath library, but there are other libraries available. In the second video, we talked about creating our own functions, either void functions or value returning functions. And then in the third video, we talked about more advanced topics such as pass by reference and function overloading. So in this last video, we're going to talk about the concept of a recursive function. So recursion can be defined as when a function calls itself. And there are some problems that lend themselves to this kind of solution. So basically, if you have a problem where you can reduce the number of cases by one each time by calling the function on a diminished version of what you originally sent it, and I'll explain that in a minute because that sounded confusing, then you can do recursion. So a good example here is a factorial. Okay, so if we have 6 factorial, it's equal to 6 times 5 times 4 times 3 times 2 times 1. Okay, and we could certainly put this into a for loop, for our int I equals, could go backwards, 6 as long as I is greater than or equal to 1, then do an I minus minus. Okay. Do that, no problem. And then we can in here just say I would have had to have int f. I could say f is going to be equal to f times I. Okay. I would have to set them equal to 1 to begin with. But yeah, basically that should go through and that should calculate the factorial. Okay, so not too bad. Okay, so we would call this an iterative approach. Okay, so this is the iterative factorial. Okay, so instead of doing it in an iterative fashion, to do it in a recursive fashion, we have to think about the relationship of the factorials. Okay, so to do this, we can look at this, and if we're going to write 5 factorial, it's equal to 5 times 4 times 3 times 2 times 1. Okay. And what you should notice is that this is equal to this. Okay. Which allows us to rewrite 6 factorial as 6 times 5 factorial. Okay. So that gets the idea of how we're going to do this. Okay. So if we have a function to create or to determine the factorial, okay, we can just, it'll take an n. We can then call, so let's spec this out. So we have an int factorial that takes an int n. Okay. Then we can just return n times the factorial of n minus 1. Okay. So that should get us the basic idea here. But there's a problem. If we were to run this, then with 6, for example, it would say for 6, well, let's return 6 times 5 factorial. Okay, so it would stop what it's doing, create a new version of factorial with 5. Okay, so 5 factorial is equal to 5 times 4 factorial. Okay, go all the way to the factorial of 1. Well, the way it's written now, it would say the factorial of 1 is going to return 1 times the factorial of 0. Okay. And there's no factorial of 0. So we hit a problem. Okay. So the other problem is it's going to go forever. It's not ever going to stop. Okay. So if we're going to do this, we have to have some base case. So the base case is where the recursion ends. Okay. It's basically a value that we know the answer directly. Okay. So in the case of factorial, we know that that 1 factorial is equal to 1. Okay. So when we get there, we know that we're done. Okay. So this allows us to do the following. And whenever you have a recursive algorithm, it's important to think about this. You first have the base case. Okay. And you're always going to have an if. So we're going to say if n is equal to 1. Okay. Then we're going to just return 1. Okay. That's all we're going to do. Okay. We have an else now. Okay. And this is, we could call it the recursive step. Recursive step, we're going to call this. Okay. So this should work properly and it should be able to um, get us what we need as far as the values. Okay. So we can take a look at how this operates. I've got an actual function that I've written. So let's take a look over on the server. Okay. So a couple of things here. The first thing is you'll see that I'm including the myutils that we talked about in class, and the myutils in particular has this get int function, which allows us to keep the user in a loop until they enter something that is correct because it's an integer. Okay. So I'm starting here with the function prototype, okay, that goes before the int main, where I'm saying int factorial just takes an int. You can put int in if you want, but you don't have to since it's the prototype. Remember, the prototypes have a semicolon at the end. Okay. So let's look at the function, then we'll go down to that. So we have our int functions, what we just saw, kind of. We're saying the int factorial of an int of n. I'm going to go ahead and throw this in. We have to have a check somewhere, but the check should be in the function. If n is less than 1, I'm just going to return negative 99. And that's a kind of a common way that programmers let you know something's wrong. So if I enter a negative 4 factorial, it's going to, or a 0 factorial, it's going to return negative 99. Okay. I probably should print a message out as well, but for this example, I'm not going to. Okay. So this is the main part. If n's equal to 1, we're going to return 1. Else, we're going to return n times the factorial of n minus 1. Okay. This is our base case, and this is our recursive step. Okay. So when we run this one, we should get our correct answer. And you should know in advance or look up that 6 factorial is 720. Okay, so let me compile this. Okay, let me run it. Enter a 6. Gives us that 6 factorial is equal to 720, which is correct. Okay, so all that's fine, and it happens really quick. Okay, but it's important to kind of know what's happening as far as the memory goes. And that gets to kind of the problem sometimes that we can have with our recursive algorithms. Okay. So let's take a look down here with what happens. Okay. So we have our main memory that's been allocated. Okay. And then we have the stack. We haven't talked much about the stack, but the stack is a place for where we can, when we add memory while the program's running, we can add it to the stack. Okay. So when we first run the factorial, okay, on 6, let's say, okay. Um, no, actually, it starts up here. So it's up the top of the stack and moves toward the bottom. Okay, so I've got that wrong. Okay, we start with the factorial here. Okay. Um, when we call factorial on 6, 6 is not the base case. Okay, so it's going to stop what it's doing. It's going to allocate memory for 5, and then for 4, and then for 3, and then for 2, and then for 1. So by the time it gets to this point, and again, main probably is on top. I think I've got that part wrong. But by the time it gets to this point, all of these versions of factorial are in memory. Okay. It's only when we get to the base case that we can start, freeing this memory in essence. Okay. And then as we go down, we would keep collapsing each of these as we go. Okay. So that's the idea. So that leads to one of the problems that we have with a recursive algorithm is that it can take a lot of memory. Okay. Depending on how you're running it. If you don't have a base case and it starts going forever and ever and ever, you can very well run out of system memory by creating too many versions of it. I think in C++ on our system, you tend to get an infinite recursion warning before you get there, or sometimes you'll get a attempted stack smashing warning. Okay, but it's not a good thing for sure. Okay, so if you're in a memory constrained environment, it's certainly something to think about. Okay, um, another potential downside to recursion is that the programs themselves can be a little harder to read. They're not quite as clear when you're looking at them as the iterative case would be. I mean, the iterative case is pretty straightforward what's happening, and you know what the boundaries are. Okay, but down here it's not quite as clear. Okay, and then the third issue is one of performance. Since we're having to create, we have to allocate new memory every time um, and manage all of that. If if factors are such that performance is an issue, it could certainly slow you down. Okay. In our case, with this small example of factorial, we don't have to worry too much about it because we're not doing big numbers and it's not a big recursion, but it certainly could be an issue. Okay. There's a warning here when you're writing a factorial program, whether it's iterative or recursive, and that's that factorials get really big really quick. Okay. So if you're using integers, you're going to very, very quickly run out of space. Okay. And start getting into those negative numbers when it wraps around. C++ also gives you a long int, which is bigger, and a long, long int, which is even bigger. So it gives you more capacity, which may be the way to go. Okay. And then again, the way that you would code that instead of saying int, you could say here like long, long int. Okay. That would be the return type. Okay. Which should give you a little more room, a little more space. Now, the value you send is not going to be bad typically, but it's the result. Okay. So you could do something like that if necessary. Okay. So this, for real, this time, ends our discussion of functions. So it's hard to imagine there being any program that you're going to write moving forward that doesn't use multiple functions. So we know in C++ we have to have an int main. There's no if the program runs, if it's an executable, it has to have an int main. But it's really it's almost inconceivable that you can have all but the simplest program that's not going to involve functions and often a lot of functions. Okay. Again, functions allow us to modularize our program, to break it into pieces. It allows us to not have to repeat the same code over and over, and therefore introduce the possibility of there being errors. Okay. Makes it easier to read, easier to understand, gives us more control over what's happening. Okay. So functions are definitely worth learning. So hopefully these videos have been helpful in getting you a better understanding of that.